The third question that we have been given two circuits. For each of the two circuits, we need to find out the equivalent resistance between A and B. So let us begin with the first part. In the first part, we have been given a circuit which looks complicated, and people may get confused by this, but this is actually a very simple circuit. This has just been drawn like this to confuse you. So what you do in these type of questions is that whenever you get confused, you mark the points with the different potentials. All these points are with potential A. This is a point with a different potential, that is C, so I marked it as C. Now to simplify the diagram, you mark A on one side, C on one side and B on one side. Now draw all the resistances between the various potentials. We have one resistance between A and C, so we draw one resistance between A and C, R. We have another resistance between A and C and another resistance between A and C, so we draw two more resistances between A and C. This is A, and we have one resistance between C and B. Therefore, we draw one resistance between C and B. Therefore, we just now both these diagrams are totally equivalent. But this appears to be confusing, and you are not able to find out the R equivalent. But from this diagram, you can clearly find out the R equivalent. So, using this diagram, we can now easily find out these three resistances are in parallel. The resultant will be equal to R by 3. Try to learn these shortcut tricks directly whenever there are two resistances of equal magnitude in parallel. This is R, the resultant will be equal to R by 2. If there are three such resistances of equal magnitude, then it will be R by 3. So, I directly wrote this as R by 3. Now this R by 3, again replace it by R by 3, and we have another R over here. So the equivalent of these two will be equal to 4R by 3 between A and B. Since these two are in series, we add them up. Therefore, the final answer for the R equivalent in first case comes out to be equal to 4R by 3. Now let us look at the B part. In the B part, this is a typical and interesting question. In these type of questions, you should also look at factors like symmetry and such things. It eases out the question. So the first, in this question, we see that each of the resistances are equal to R. We need to find out the equivalent resistance. Now, one thing you should notice in this question is that there is no biasness between this point C and D. The points C and D are totally similar. There is no difference between these 2 points. So whatever will be the potential at C, it will be equal to the potential at D, because there is no biasness. When you apply a potential across A and B, these points C and D are totally similar. Therefore, the potential at these points have to be same because there is no biasness. So, if these 2 points are same and their potential is same, therefore these 2 points can be joined. Just fold this and join, because there will be no difference in the currents passing or anything if we join these 2 points. Since these 2 points have, I again repeat, since these 2 points have the same potential, if we fold and join these 2 points, there will be no effect on the currents passing through the circuit or anything else. So let us join these 2 points. So what we get is that AB, we have this parent circuit remains like this for the lower part. Now this, we have another resistance between these 2 points, another resistance between these 2 points, and another resistance between these 2 points. So this becomes our equivalent circuit where each of the resistances are equal to R. Now this resistance is R, this resistance is R, and these two are in parallel because they are across the same potential difference. Therefore we can replace them by R by 2. So this becomes R by 2. Again R in parallel becomes equal to R by 2. I write this as R by 2, and these two also I write them as single R by 2. Now this is equal to R, this is equal to R. You have to be very careful at every stage. Now what you can, to solve this question now again very easily, what you have to look over here is that this is a Wheatstone bridge. You have to visualize this as a Wheatstone bridge. Let me redraw this so it will be easier for you to locate a Wheatstone bridge. this resistance R comes over here, this resistance R comes over here, this R by 2 remains over here, and this R by 2 remains here, and this is R by 2. Now this is clearly I have just pulled this point and placed it over here. There is no harm in that. Now we see that the product of these two is equal to the product of these two. So that is the case when Wheatstone bridge is balanced. Therefore no current will pass through this wire, and therefore this wire can be removed. Any wire through which current does not pass can be removed. Therefore our equivalent circuit becomes like this. Now these two are in series. Therefore this becomes 2R over here, and this 2R is in parallel with R by 2 plus R by 2, that is R. Now the equivalent of 2R and R in parallel will be 2R into R upon R plus R upon 2R plus R, R1 R2 upon R1 plus R2. Therefore this becomes equal to 2R square upon 3R, that is equal to 2R upon 3. So final answer for the R equivalent in this case came out to be 2R by 3. We just used two tricks of, if the potential of the 2 points are same, we join those 2 points by folding this loop, and we use the concept of Wheatstone bridge to find out the final answer as 2R by 3 in second case and 4R by 3 in the first case.